What specific problem does the proposed LLaVA-o1 method aim to solve in multimodal reasoning, and why does it matter in the context of existing vision language models?
The proposed LLaVA-o1 method aims to address the inadequacies in the reasoning processes of existing vision language models, VLMs, particularly their tendency to produce errors or hallucinated outputs due to insufficiently systematic and structured reasoning. Traditional VLMs often generate responses without adequately organizing the problem or the available information, leading to premature conclusions and flawed reasoning paths. LLaVA-o1 introduces a structured multi-stage reasoning process that includes distinct stages: summary, caption, reasoning, and conclusion, which enhances the model's ability to engage in systematic and in-depth reasoning. This structured approach is crucial as it significantly improves performance on complex reasoning tasks, making LLaVA-o1 more effective than traditional chain-of-thought prompting methods. Ultimately, this advancement matters because it enhances the reliability and accuracy of multimodal reasoning, which is essential for applications requiring logical analysis and interpretation of both visual and textual information.
Can you break down the LLaVA-o1 algorithm step by step, detailing how it processes the four distinct reasoning stages: summary, caption, reasoning, conclusion, and the significance of each stage?
The LLaVA-o1 algorithm processes information through four distinct reasoning stages: summary, caption, reasoning, and conclusion. In the summary stage, LLaVA-o1 provides a high-level overview of the question, outlining the key aspects it will address, which sets the context for the reasoning process. The caption stage follows, where the model describes relevant visual elements from an image, if present, ensuring that multimodal inputs are effectively integrated into the reasoning. Next, in the reasoning stage, LLaVA-o1 engages in structured and logical analysis, systematically considering the question to derive a preliminary answer. Finally, the conclusion stage synthesizes the information from the previous stages into a concise response, adapting the output based on user requirements for detail. Each stage is crucial as it allows the model to maintain clarity and organization throughout the reasoning process, ultimately enhancing its ability to perform complex reasoning tasks effectively.
Provide a simple yet illustrative example of how LLaVA-o1 would generate responses through its reasoning stages for a specific visual question, explaining each step with the appropriate tags.
For a visual question such as, "What is the color of the car in the image?" LLaVA-o1 would generate responses through its structured reasoning stages as follows. 1. Less than summary greater than. In this stage, LLaVA-o1 would summarize the task by stating, "The question requires identifying the color of the car depicted in the image." Less than summary greater than. 2. Less than caption greater than. If the image is present, the model would describe relevant visual elements, such as, "The image shows a car parked on the street surrounded by trees and buildings." Less than caption greater than. 3. Less than reasoning greater than. Here, LLaVA-o1 would analyze the visual information systematically, stating, "The car appears to be red based on its surface color and reflections." Less than reasoning greater than. 4. Less than conclusion greater than. Finally, the model would provide a concise answer, such as, "The color of the car is red." Less than conclusion greater than. This structured approach allows LLaVA-o1 to maintain clarity and logical flow throughout the reasoning process, enhancing its ability to provide accurate responses.
What advantages does LLaVA-o1 offer over traditional chain-of-thought reasoning methods, particularly in the context of handling complex reasoning tasks?
LLaVA-o1 offers significant advantages over traditional chain-of-thought (COT) reasoning methods by implementing a structured and systematic approach to reasoning. Unlike conventional COT, which allows for free-form thinking, LLaVA-o1 organizes the reasoning process into four distinct stages: summary, caption, reasoning, and conclusion. This multi-stage framework enables the model to maintain clarity and coherence throughout the reasoning process, effectively addressing complex tasks that require systematic analysis. Additionally, LLaVA-o1 employs a novel stage-level beam search method, which generates multiple candidate results at each stage, enhancing performance reliability and scalability. Experimental results demonstrate that LLaVA-o1 substantially outperforms traditional COT prompting, particularly in complex reasoning tasks, by ensuring that the model engages in a structured thought process rather than prematurely concluding without adequate justification.
Describe the experimental design used to validate LLaVA-o1. What datasets were used for testing, and what metrics were employed to measure its performance?
The experimental design to validate LLaVA-o1 involved comparing its performance against the base model, LLaMA3, 2-11B Vision Instruct, across 6 widely used multimodal benchmarks: MM-STAR, MM-Bench V1, 1 MM-VET, MathVista, AI2D, and HallusionBench. These benchmarks were selected to evaluate various capabilities, including general visual question answering, mathematical reasoning, and handling language hallucinations. The performance metrics employed for measurement were derived from VLM-EvalKit, an open-source evaluation toolkit specifically designed for large vision language models. Additionally, ablation studies were conducted to assess the effectiveness of the LLaVA-o1 to 100K dataset and the structured tags used in the model, further validating the contributions of each component to the overall performance. The results indicated that LLaVA-o1 achieved significant improvements, with an average benchmark score increase of 6.9% compared to the base model, demonstrating its enhanced reasoning capabilities.
What limitations or potential drawbacks does the LLaVA-o1 model have, particularly regarding its practicality, complexity, or general applicability in real-world scenarios?
The LLaVA-o1 model, while demonstrating significant advancements in structured reasoning, may face limitations in its practicality and complexity. One potential drawback is the reliance on a specifically curated dataset, LLaVA-o1 to 100K, which may not encompass the full diversity of real-world scenarios, potentially limiting its general applicability. Additionally, the model's structured reasoning process, which involves multiple stages, summary, caption, reasoning, and conclusion, could introduce complexity that may hinder its efficiency in time-sensitive applications where rapid responses are required. Furthermore, the model's performance is contingent on the effectiveness of its stage-level beam search method, which, while scalable, may still struggle with open-ended questions or scenarios that deviate from its training data. Lastly, the necessity for extensive computational resources during training and inference could restrict its accessibility for broader use in various practical applications.